Hello, my name is Neve. I'm the team lead for StrathSEDS entry into the Mach 22 launch competition this year. I hope you enjoy our CDR, and we're going to kick off with Matthew, who's going to be doing our launch vehicle overview.
Hi there, I'm going to show you through our launch vehicle overview. So this is Stratosphere 1, the final design iteration of our launch vehicle for the CDR. In this side-on view, you can see the general configuration of the components on the rocket labelled. The rocket currently stands at about 1.1 meters in length. In the following slides, we're going to go over these components of the rocket in more detail. Well, first off, what has changed since the PDR with our launch vehicle? First point is strain gauges. The strain gauges were proven to be a very difficult task to integrate into the rocket body, and accessing them while inside the rocket was proving extremely challenging to design around, and therefore we came to the decision to remove them from our mission. This also allowed us to keep avionics inside the nose cone. And due to factors like increased mass, differences in payload configuration, and increased drag from fin sizing, we've changed our chosen motor from a Cesarone i287SS to the 548 i242 motor. The latter packs roughly 100 Newton-seconds more impulse, which allows the rocket to still reach 1 kilometer apogee in its current design state with max payload. And due to this, we have also included more centering rings to ensure airframe integrity. The motor is now also slightly more expensive than the previous motor because of this. Another update is our main body and motor mounting tube material. Previously, blue tube was going to be used, but due to that only being available on the Apogee Components website, who were not only out of stock, but also had a lot of logistical problems shipping from America, we've switched to using phenolic tube for both. This is our nose cone. Our nose cone on the surface has not changed at all since the PDR. We're still using 150mm length by a 78.7mm external diameter with a 50mm collar going into the rocket. The nose is currently still being manufactured using a 3D printer, a lot like our other components, but if the nose needs elongated at all, we may need to find another way, as the current height of the nose takes up almost all the height in the printer. Taking a look inside our nose now, there's a few new additions. We've designed an avionics bay, which includes an 18650 battery, an Adafruit GPS unit, and a PCB designed by the electrical team. So the nose cone has been designed to include a hard point for the eye bolt to mount onto, as well as 2 epoxy threaded rods to act as hard points on which the avionics can slide in and out on. During the flight, the avionics will be bolted on here so that they're not lost on payload ejection. I'm now going to pass you on to Barnaby to take you through the rest of the rocket components.
The first component of the outer side of the rocket is the group of fins. All 4 fins are 3D printed at the same time using PLA+, and they fit in place around the motor mount, held in place by 2 centering rings either side. We decided on the shape of the fin due to the flat base on the right-hand side of the top right image will be the base of the print, and the sweep produces less drag at the outside edge of the fin. And it also uses less material than a square-shaped fin. We chose the NACA 002 aerofoil because it's a simple symmetrical aerofoil which performs better than a flat plate at high speeds. The motor mount is made to encompass the Catharoni motor entirely and allow for discharge of the ejection gases through the top of the mount. The hole is not shown in the images here. To retain the motor, we'll use the Apogee Components 38mm flat bottom retainer, and this will attach to the aft centering ring to prevent damage to the airframe of the rocket. The centering rings on our assembly, there are 4 of them, and the one at the top of the thrust assembly has a hole in to accommodate a 6mm eyelet for the shock cord to loop through. We've decided to use a phenolic tubing for our airframe and our motor mount because it's easy to acquire, cheap, harder than paper, and more water resistant than paper, which is extremely important launching on the west coast of Scotland. After looking at the technical guidelines, we agree with your recommendation to use the 1-inch launch buttons. We'll acquire these from Apogee Components, or we can mill these ourselves at a university lab. Stratosphere 1 has a total mass of 1.9 kilograms, plus a total payload mass of 1 kilogram split across the 2 CAN sets in the center of the image. The center of mass of stratosphere, fully loaded, is shown with the blue and white circle. Looking at the flight safety analysis, through simulations on OpenRocket, we found that Stratosphere 1 is capable of flying safely at wind speeds of 21 meters per second or 46 miles per hour. We discovered this through simulating all winds in 3 meter per second increments up to 27 meters per second or 60 miles per hour, and measuring the drift and the apogee of each launch. Looking now at the stability of the flight of Stratosphere, we found that it leaves the launch rod at 26.4 meters per second, accelerating at an average of 89.9 meters per second. This acceleration equates to about a 10G acceleration on the rocket. In the technical guidelines, it was suggested that our rocket should satisfy all 4 assumptions for slender body theory, this being a high length to diameter ratio, a high normal force coefficient, a subsonic speed, and thin fins. We satisfy 3 of those 4 conditions. The length to diameter ratio is 13.34, the normal force coefficient is 17.4, and our maximum speed unloaded without a payload is 250 meters per second, which is less than Mach 1 in all temperatures and pressures that you normally find up to about 2 kilometers. The one assumption we cannot satisfy is the thin fins, because it's not really possible in real life to have a thin fin with 0 thickness. However, the thickness of our fins is rather small compared to the diameter of the rocket. Finally, looking at the static margin, it's found that with a full payload, it has a static margin of 2.36 diameters, and without a payload at all, it has a static margin of 1.72. This means that with or without a payload, Stratosphere 1 will fly safely and will reach its target altitude. Both the static margin and the normal force coefficient will be verified with either computational fluid dynamics or a wind tunnel test. We have received permission from our university to use the wind tunnels on our campus. And finally, looking at the impact on our design that flight analysis has had, we have had to adjust the fins to satisfy the required range of normal force coefficient. Before adjustment, we had about 10 in this coefficient, but now, as shown in the image in the middle of the slide, the fins have a coefficient of 15.4 and the body itself was 17.4 overall. And in the enlargement process of our fins, we found we pulled the static margin quite far towards the aft of the rocket. So we had to push this forward. And to do this, we moved the fins towards the forward end and reduced ballast in the nose. Finally, our motor is the Cesaroni 548 I242 W815A13. It has an impulse of 548.2 Newton seconds and a max thrust of 284.7 Newtons. Again, this max thrust equates to about a 10G acceleration. The thrust curve of the Cesaroni 458 I242 is shown on the slide here. We have not yet ordered the motor due to budgetary constraints. I will now pass you back to Matthew for the details of the recovery subsystem.
Our rocket recovery system is also similar to what we use in the PDR. I'm going to start by covering the ejection. So our OpenRocket file recommends using an 11.9 second ejection charge with our payload. Using resources we've found online, we used an equation to find the internal pressure needed and then a gas equation with relevant constants to find the mass of black powder we needed for ejection. The mass came to only 0.24 grams, which feels low, but as none of us have any experience with it, we're unsure whether this is in the right range or not. We're making the assumption here, or many assumptions here, that ejection is frictionless. The exit velocity of the payload is 10 meters per second. It has a distance of 0.6 meters to accelerate over, and the total ejected mass is 1 kilogram. No electronics are being used in our ejection mechanism. We're relying solely on the delay inside the motor. After the charge goes off, the pressure inside will push the aluminium block forwards, and this will go through the rocket tube, which in turn pushes the rocket parachute, both CANSATs, and the nose cone out the front of the rocket. The aluminium block is linked to the rocket shock cord system, which joins the motor mount and the body to the block, and then through the block it joins to the parachute and then up to the front of the rocket to the nose cone. Now I'm going to touch on some of the descent information for the rocket. We chose a parachute to use, the BCC-24 parachute from Black Cat Rocketry. It's a 24-inch diameter parachute with a spill hole, and it also comes in a range of nice bright colors to help locate it in the earthy yellow-green fields, something we struggled greatly with last year. Using open rocket simulations, we tested a range of wind speeds for drift calculations. So long as the wind is less than 12 meters per second, our drift should be less than 1 kilometer according to the sim data. I should note that the numbers provided for the apogee and optimum delay time here are for an unloaded rocket. We did this way as we were unsure about how OpenRocket calculated these numbers with the internal payload and whether or not that would be ejected at the sim or at the sim apogee. Given the apogee would be lower in the real flight with the payload, then the drift would also be reduced slightly.
So, as for ground control system design, the approach that we described in PDR hasn't changed much. We are still aiming to create a mesh network with at least 4 nodes that will allow us to overcome limitations of traditional point-to-point radio communications. Our design specifically for the ground stations changed only slightly. We are skipping the step of a microcontroller translating the radio signals from our radio modules to our processing computers, and instead we're going to be connecting the radios directly to the processing computers using simple UART to USB converters. The radio modules will be using most likely a Yagi antenna that is still not decided. We are aiming to use a high gain antenna, which is why we are most likely be using a Yagi antenna, but due to our delays, we have yet to secure a single antenna product, or we are even considering making an antenna on our own. As far as the radio modules, this again has not changed since PDR. We are going to be using the XB-SX868 modules. They are going to be working at 869 megahertz, the channel 29 or 28 as specified in their documentation. This is mostly because we want to use the highest available duty cycle in this frequency range as specified by Ofcom. And at 869 megahertz, this is the highest duty cycle of at least 20%. This is all handled by the radio module as it is certified to work in the UK as seen in the certification down below. For the ground station, as I said before, we're going to try to use a high gain Yagi antenna, but for the rocket and our payload, we will be using a quarter wave wire antenna. Those usually come with a gain of around 3 dBi, which should be sufficient to work over at least 5 kilometers.
I'm going to touch on the mechanical design of the payload now. First is any changes we've made since the PDR. The only large changes on the CANSAT since the PDR are a standardizing of our dimensions. We found that we were all working on slightly different numbers for diameters and lengths, and these dimensions have been set for the CDR and are unlikely to change again given we don't require any more room internally. Another change is the configuration of the internal components, with battery holders now included as well as an accurate model of the PCB and a GPS. We realized that we had to reshuffle the internals quite a bit to fit everything in there. Other than this, not a lot of the CANSAT has changed. So, this is an overview of our CAD model. A lot of parts of the CANSAT we're 3D printing, as this is very little logistical issue since we can print pieces ourselves. The only pieces of the CANSAT not 3D printed are the metal pieces, being the 5mm threaded rods, the nuts and washers, as well as the M4 parachute eye bolt. On the next slide, we have detailed the side and front-on views of the CANSAT with labeled electronics. You can see the positions and orientations of all the components on the CANSAT. It is clear to see here that the eye bolt has been offset to the opposite side of the GPS, and this is so that it interferes as little as possible with the operation of the GPS, as a piece of metal directly above it may interfere slightly. Also on this slide is a dimension drawing featuring a few of the relevant lengths and diameters. You see that in the middle. Now onto the ejection system. On the left, here is the stowed configuration of the payload. The CANSATs are separated by small tubular spacers that wrap around threaded rods, and these prevent the CANSATs from punching into each other's shells on deployment. It's not fully decided at this point, but these could either be reusable and attached to the lower CANSAT's parachutes, or be discarded on deployment. In the latter case, we would be using a cheap but biodegradable and sustainable material. It'd be easy to make them from plastic, as we could just 3D print them, but we neither want to pollute the environment with wasteful pieces of plastics, nor do we have the budget to deal with the extra £80 fixed penalty notice. As was covered in the ejection section of the launch vehicle slides, the ejection charge will push the aluminium block down the tube along with the rest of the payload, clearing the main body tube. Recovery welding is going to be used between the front CANSAT and the nose cone, so that when all the payload is pushed down the tube, the nose cone will be able to eject off the front undamaged by a half-kilo CANSAT hurtling towards it. So to continue onto the descent system, the planned parachutes will be 12-inch Black Cat rocketry parachutes. There is no dedicated parachute deployment mechanism for the CANSATs. We're relying on the parachutes to naturally begin deploying, and then for the airflow to bring them to full deployment after that. After both the CANSATs have been ejected, their parachutes fully deployed, the rocket and two CANSATs should all be descending individually under their own parachutes.
So now proceeding to our electronic design. Last time on PDR, we mentioned we will be using the STM32F405 microcontroller, but we had to change that slightly due to chip shortages and availability at our manufacturer's site. This time, we are centering our design on an STM32F411, which is very similar, only with a slightly slower speed and a little bit less pins. Our schematics are 100% complete right now, surrounding the microcontroller, as well as the design on the PCB for necessary components, such as the crystals. This is all following specific guidelines for all of those components as specified by ST Microelectronics. This gives us high confidence in the working of our design, which we will try to confirm with rigorous tests once we actually get to manufacture them. And now we will be proceeding to the power design of our board.
This is the rectification circuit, which provides the reverse connection protection and also overcurrent protection. It also allows both the USB 5 volts to be used while the batteries are connected without messing with the charge levels on the batteries. Now, this is the other half of the circuit, the regulation circuit. The power regulation from the variable 4.7 volts down to 3-ish volts is done by a TPS 7333 QDR IC by Texas Instruments. It also will regulate current to 500 milliamps, but I didn't want to rely on that, so there's an extra fuse there as well. It also includes a red LED to indicate if it's powered up or not. And it currently has a reset and power enable pins. Those can be used to create a over discharge protection circuit. That's not implemented yet, but it will be in a future revision of the board.
So for pressure sensor, we're using the BMP388 altitude temperature sensor. This measures static pressure, so we do not need to worry about the location of it within the board. We're also going to be using the BMI 055 IMU with an accelerometer and gyroscope. We did want to take a more advanced version, which would have a 9-axis sensor system and include a magnetometer, but we were unable to attain this due to the ongoing chip shortage. We're going to include a buzzer on the CANSAT and rocket for ease of finding the rocket once it's landed. The buzzer can go up to around about 100 decibels and can be adjusted in pitch and frequency to something hopefully not deafening. There will be a set of LEDs included on the board that will be used for indicating specific cache settings and debugging.
Also on the board, there will be a variety of headers and connectors. So the GPIO pins, shown in the top right, will be used for general debugging and testing. They're going to include, as you can see in the schematic, they're going to include a couple of just GPIO pins from the MPU that can be assigned later, the reset and power enable for prototyping, and various, voltages and grounds. Then we have the 3 connectors for the GPS, the ST-Link, and the strain sensor. Note the strain sensor has since been removed. This is an old schematic. We also have a 2-pin power connector for plugging in the battery that is distinct from all of the other connectors, so there's no accidental misconnections. Also note that all of the connectors, bar the GPIO pins, are keyed, so we can't plug them in the wrong way. We also have an SD card and a USB connector. The SD card will be for storing data that we aren't going to send and to have a backup in case something goes wrong with the radio. The USB will allow us to communicate more easily with external devices, as well as being able to power the board for debugging and testing.
So, wrapping up, we are roughly 90% complete in terms of our electronic design. The schematics are all completed, the components have been chosen and secured and confirmed to be in stock with our manufacturer. We have completed almost everything on our PCB design, as shown on the slide, barring a few minor components like user switches and capacitors for the boot sequence for the MPU. That's why we think we will be able to complete the PCB design in the coming week. That will allow us finally to order the version 1 of our mainboard. Going over the next slides, as you can see, different layers. This is the top side of the PCB. We opted to go for a 4-layer design. This allows us to route the traces more easily, connecting to power only using simple vias. This is the underside of the design, where we place the radio and the SD card. And we managed to make also a few 3D renders of our design. This is especially useful for coordinating with our mechanical team. Those designs, those 3D designs are likely very close to final, just as I mentioned, barring a few minor components. This is the underside of the PCB.
So we're going to start the power budget off with the source. The source is an 18650 lithium-ion battery, and we're going to have 2 of those. So each one is 2.6 amp hours of capacity. Double that, that's 5.2 amp hours. And each is running at operating voltage of 3.7 volts. That will go up and down depending on the capacity, where it is on its capacity. And so that gives a max theoretical capacity of about 9.62 watt hours. We don't want to use that much because we want to let these cells last as long as possible. So we'll try and limit it to only using about 7 or 8 watt hours. And it's got an operating temperature of up to 60 degrees C that we're going to try and stick to. So I went through each component in the power budget, added them up, their currents up, and I got a figure of 250 milliamps continuous for the worst case, with everything on all the time and the buzzer going full blast. And then using different duty cycles for each component, I've created an average power, which was 544 milliwatts averaged, which is tiny compared to our capacity. And when you plug those in and look at the actual on time possible, with the average power is over 28 hours. So as a sanity check, I've included just the non-average direct current was over 16 hours. So insane, plenty of time for our purposes. The worst case, the highest current it could possibly pull in like normal running, well, not even normal, was running for about 7 hours. So this is each component, their duty cycle, their currents, predicted currents, and the average power. So the conversion efficiency column, basically some are after the regulator, and the regulator has some inefficiencies inherent, and some are before, like the buzzer and the battery. And so the three main components here to note are the buzzer, the radio, and the strain sensor. So the buzzer is only going to be on when the rocket has landed and the CANSAT has landed, and that has the highest current. The radio is the second highest current, but it won't be transmitting for that much time. And the strain sensor has since been removed. It's not been removed in this power budget, but you can see that the current drawn is minuscule, so it really won't affect things very much. And here is the lifetime raw data. You can see that the average time for the median was about 60 hours, which gives us plenty of time for anything we could possibly want to do. So kicking off the electrical testing, we have the thermal tests. So the regulator, when it is putting through a lot of current, will itself have a lot of power across it. And that will cause it to heat up. So we're going to test it by drawing a high current and checking that it's not exceeding its specifications. Also, when the ejection charge goes off, there'll be a lot of hot gases going through the rocket. The CANSAT is pretty isolated from that. We just want to make sure that the actual cells themselves aren't heating up too much, which could cause them to fail, which would be bad. The next test we're going to do are the power delivery tests. So there's a lot of these here, so I'm just going to skim over them. Continuity, just make sure everything's connected the right way. Fuse, make sure that when we try and draw too much current, the fuse will stop, and then it will reset properly without any external influence. The current limiting of the regulator, noise ripple, basically that there's not too much noise on the power rails. Check that the voltage inputs of the 5 volts will not mess with anything, and that the regulator can smoothly accept changing inputs. And the reverse polarity protection, basically rewiring the plug in the opposite direction and making sure that that protection functions as expected.
So, as far as our radio tests go, we plan to perform a few range tests of our radios. Obviously, once we receive our radio modules, they will be extensively tested on close distances, or rather on our bench, to confirm that we can transmit data in all directions and confirm that the mesh configuration of the radios is working. We will be doing extensive configurations using the provided XCTU software by XB. But once we confirm that the radio modules are working, we will be going forward with our longer range tests, starting with short range tests, and those will be tested on around 1 kilometer max. Then we are looking to move to our local mountain range, specifically Damgoin, that will allow us to have great line of sight visibility. And using the map shown on the slide, you can see that we are looking to perform a range test as long as 5.7 kilometers. We will be doing a continuous range test, so we will be tracking the location and signal strength of a node that is going away from Damgoin, and we will try to see where or if the signal cuts off and how that coincides with our expectations from the radio modules.
Okay. For the IMU, we have 2 tests of testing to be done on it, gyroscopic and accelerometer. For the gyroscope, we're going to turn it 90 degrees to check if its orientation works correctly. And for the accelerometer, we are going to move it specific distance at specific rate to ensure that the acceleration is calibrated correctly. For the pressure sensor, we are hoping to get access to a barometric chamber, but failing that, we have a plan to take it up a hill to check if its altimeter sensing systems is working correctly. For the pressure sensor's temperature sensor, we are going to put it in an enclosed space with a known temperature gradient across it.
So I'm now going to be taking you through the additional testing plan for the mechanical subteam, which primarily consists of structural tests. As with the electrical team, not been able to carry out any testing yet, just mostly due to budgeting constraints, but we hope we'll be able to begin manufacturing, therefore testing within the next couple of weeks. So if we start with airframe tests, we're going to start with a mortar mount load test, which will have a dummy rocket body with the mortar mount inside. We're going to apply first 10 Gs of force to it laterally and axially, and then 20 Gs. This is just to make sure that when we remove the mortar mount, there's no cracks or deformation, and we know that it'll be able to withstand the forces of launch. After this, we're going to be doing a vibration test where the rocket's strapped to a vibration table and all of the electronics are turned on. We're also going to remove the motor for this just for safety reasons. We don't want pyrotechnics rattling about inside the lab. The vibration table will be switched on for the expected flight duration times 1.5, just to give us a bit of a buffer, just to make sure. And we hope that the result of this is telemetry is still able to be received during the vibration test, and that afterwards, when we inspect it, there's no structural damage. After this, we'll also be doing a drag test with a wind tunnel, just to make sure that the drag observances we see line up with what we've calculated on paper. So next we have our ejection deployment recovery tests, which is really, really important. So we're going to start off with some parachute tests for both the CANSATs and the rocket, which is going to basically be folding up the parachutes the way they will be on launch day and throwing them off the bridge to make sure that they unfurl the way they're supposed to, and that they descend at the rate that they're supposed to. After this, we're going to have a bit of a day out in the field and do some hide and seek, as well as some of the electrical team testing. So for this, one member of the team, like for me, is going to take the CANSATs on the rocket, put them in recovery mode and hide them in a field with long grass like they are at Mach. And then the rest of the team are going to use only what they'd be allowed to use on launch day, so our ground station, to find both the CANSATs and the rocket. Hopefully the buzzer will be plenty loud enough to locate it, and receiving GPS data and everything works. But we're also going to do this test without the ground station to see how quickly we can find it with just the buzzer. Then we're going to be doing an ejection test. So we'll remove the motor mount so that we can set up a device in its place at the bottom of the rocket that simulates an ejection charge. That's because we're not allowed to light ejection charges inside the university lab. We'll start this test with no CANSATs, just an empty rocket and the aluminium billet, and then with one CANSAT and finally both CANSATs. So hopefully we can see that the CANSATs are ejected in a safe manner and the way we expect them to be. So finally, I'm going to take you on to safety. So just going through our requirements compliance, our motor is an I-class motor and it has a maximum impulse of 550 Newton seconds, which is within the allowable. And you can see from our motor mounting section that will be mounted securely. For the performance margin, slender body theory can pretty much be applied to this rocket, and the minimum speed of 20 meters per second off the launch shroud should be obtained. And our static margin is between the recommended 1.5 and 2.5 diameters. And we're going to confirm our structural requirements during testing. Our calculations say that it should be fine, but we want to double check this with tests. And the maximum runtime with all electronics firing far exceeds the 30-minute requirement for the electrical system. So we're quite pleased with that. And for recovery, both the CANSATs and the rocket have a parachute capable of allowing them to decelerate to a speed well below 15 meters per second before they hit the ground without drifting too far. So now I'm going to be going over our failure mode matrices. So this is for our launch vehicle. So as you can see, the main things that we're worried about are kind of along this diagonal here. Starting with unexpected motor ignition. So that's before we're on the launch pad. If the motor ignites suddenly, obviously we don't want that to happen. So to prevent that, we're just going to store the motors really safely, make sure that everyone is trained on how to actually mount it, how to use it, how to treat it with care. And the other thing is a deployment failure, which is if the ejection charge just doesn't work and we can't deploy everything properly. So hopefully in testing, we'll be able to confirm that that won't happen and that it will be able to launch the way it should. Another couple of the things that we're slightly concerned about is the body structural failure during flight. So hopefully our structural tests confirm that this shouldn't happen at all. But yeah, so hopefully our tests confirm that that shouldn't happen at all. The other thing, as you can see, R7, the parachute or shock cord tearing during deployment. This is another thing we want to check with the ejection test, that there's no tears in the parachute, no weak points in the shock cord, everything works the way it should. And finally, if the GPS or radio become non-functional during flight, obviously this is a mission centered around radios, so we really don't want that to happen. But we're going to, again, lots of testing is going to be done on this one. So move on to the next slide. Our payload failure matrix, you can see it's a bit shorter. And one thing that we are concerned about is ejection from the rocket damaging the structural integrity. So the main thing we're concerned about here is the eyelet mounted on the top of the CANSAT when it hits the next CANSAT. But we're hoping that we'll be able to make sure during our ejection test that this doesn't happen. And we hope that maybe with spacers in between, it should also make this a bit less likely. Again, parachute failing to deploy, this is something that we're going to be testing, as well as with the radio and GPS failing during flight and the component mounting plates breaking during flight. We should be able to check that doesn't happen during our vibration test. So the last one from the mechanical team, the recovery and ejection one. So this is all to do with stuff like the nose of the rocket failing to deploy, parachutes not deploying, shock cards breaking, ejection charges failing, all of the kind of worst case scenarios. And again, this is all stuff that we hope we're going to be able to make sure that it doesn't happen during our ejection tests and during our drop tests. R7 is one that we are looking at quite a lot at the moment, just making sure that the parachutes don't tangle. So at the moment, we're doing a lot of simulations on that to see where they come out of the rocket in relation to each other. And we're thinking about using spacers between the CANSATs to make sure that they don't tangle with each other. So I'm now going to pass you over to the electrical team, who are going to be talking about the electrical safety.
The PCB and batteries both have inbuilt electrical protection to safeguard against faults and bad decisions. The PCB has reverse polarity protection in case the connector is miswired, and the connector itself is keyed, so you can only plug it in one way. On the board, we have overcurrent protection in the form of a resettable fuse of 1.85 amps. Is resettable, meaning after the fault current is gone, it will allow current to flow again. And it's also got 500 milliamps from the regulator. There is also over discharge protection planned for the next revision, but that's not implemented yet. On the battery, they have a small PCB, including its own protection. They have short circuit protection, overcurrent protection, which starts about 5 amps, which is very high for applications, overcharge protection, and over discharge protection. Charging of the batteries will be done by a commercial off-the-shelf charger, which will be built to standards.
So, in the electronics team, we considered a lot of different faults that could occur during our development phase of our mission or during the mission itself. As you can see, most of them have a very low probability. We positioned them there because we believe that we will be able to get rid of or isolate most of those faults during the development phase and make sure that they won't happen during the actual mission. There are a few exceptions to that though, like the fault number 1, which is the GPS not initializing. This has a considerable probability and severity, which we will try to work around as much as possible. And the other fault is R8, which is wire damage. This could happen due to wire fray. We will be trying to avoid that as much as possible using strain relief wiring. But most of our faults we will try to isolate during the development phase.
So just to finish off, I'll be going over all of the project planning for RF Magic, which I've been primarily doing. So if we start off with our budget, here you can see our project financial overview page. Since our primary mission is focused around forming an aerial mesh network, the use of 2 CANSATs is preferable over having 1 if we can afford it. Split into individual price on the left, our 2 CANSATs should cost around £500. That's combined, not each. The rocket will be around £450. Then the ground station and other small items didn't quite fit into another category should be around £200. So once we apply like a small margin for costs fluctuating and delivery costs and all that kind of thing, comes to around £1,200. So all of these values are calculated from a lot of data and a lot of Google searching for links, and you can see all of that in our appendix for the presentation. I'm not going to read out every single component. You can also see on the right there, we have a table for other costs, such as entry fees, spare parts, and outreach costs. You'll notice we haven't budgeted for travel. This is due to the fact that a large majority of the team are based in city centre Glasgow, so there shouldn't be much travelling to get to the competition bus. 5-minute walk for most of us. As for funding sources, we have 3 likely sources in the mix at the moment. So that's the Mechanical and Aerospace Engineering Department of the university, the UK SEDS project grant, and the Strath Union Student Executive Fund. I actually had to re-record this section because we just received £600 of funding from the Student Executive Fund to cover our entry fees. We really hope that this is the first of many more approved funding applications. However, in the event that we don't receive any more funding, we're brainstorming a lot of ideas, from car washes and fun runs to bake sales, and worst comes to worst, to GoFundMe. But we really hope it doesn't come to that. There are a couple of areas that we can cut back on as well, such as spare parts or going down to 1 CANSAT instead of 2. But we've learned from last year having spare parts is important. So we hope that it doesn't come to that and that we just get all the funding that we want and everything works out fine in an ideal world. I'll move on to our Gantt chart. So this is for the mechanical sub-team. So for us this week, it's mostly doing the tiny last few bits of CAD, make sure the design has everything we need, taking on any feedback we get, tweaking it, making sure that we know what we're about to start building. After that, hopefully we'll have funding, and it will be a lot of ordering components, getting materials, getting all that into the lab to get ready for manufacturing both the rocket and the CANSATs, hopefully before the start of May. This is our worst outcome. We're looking at the start of May, but hopefully before then. As you can see, we're going to be testing whilst we're building, and we think this is the most time efficient way for us to do it, but some tests will have to be done after it's been fully built. And we plan to have that done by the 10th of June, have everything built, last few tests to do, and we will be ready for launch day. So that should be very exciting.
So as you can see here, this is our revised midterm plan of our electronics development. We had to work around significant delays that happened due to delayed funding and disruptions caused by chip shortages. We had to redo a lot of our designs because chips were disappearing while we were designing all the circuits around them. But as you can see on the Gantt chart below, the debug and test of version 1 of our board is our margin of error. We will need the most time for that phase of our development, but if we were to face any more delays, we are hoping that phase would allow us to contain them before we get to preparation of V2 of our board. In the worst case scenario, we are hoping that V1 will be able to perform during our mission. So the whole section that was blocked off for making V2 of our board will not be needed. That will give us even more time to address another delay in funding or other disruptions to our development. But so far, looking at our short-term tasks, this is completing the V1 design of our PCB and working out fabrication. The fabrication is mostly, the preparation for fabrication is mostly done. We just need to make sure that our files will be accepted by GLC PCB.
So yeah, just to conclude, the major accomplishments of this team since PDR, I'm very proud of them all. There's been a lot of CAD work done on both CANSATs and Stratosphere 1. The PCB design is also nearing completion, and we finally secured some funding, which I know we're all very happy about. The next steps are just, like I said, completely finalizing all of our designs, securing the rest of our funding, making sure that we actually have the money to start manufacturing and testing. And yeah, hopefully by the flight readiness review, we'll have a full rocket to show you. Yeah, thank you for listening to our presentation. If you have any questions, feel free to send me an email. I'll make sure we get it answered. Look forward to speaking to you soon.